to consider the spin-spin interaction between individual spins, and if there is any external magnetic field is present. Now that basically needs a complete analytical solution of this thing depending on the dimension and the system symmetry. Okay, but irrespective of doing that, there are basically ways to solve the same problem without actually doing such complicated mathematics. So one approach we have showed already, that basically where we introduce the idea of a molecular field. Okay, and we have treated the ferromagnet as a paramagnet that is present in an effective magnetic field, okay, which is contributed by the external field and the internal field. Okay, so this Landau's theory also, it's another alternative approach through which this ferromagnetic behavior and ferro to para phase transition, this can be explained. So so let us see what is there in this theory. So basically it's a model. Okay, so this is used to describe the phase transition. Okay, and how it does that? It uses the free energy of the system. Okay, so it uses the free energy functional. Okay, so I hope all of you know what is a function, what is a functional, right? Okay, so what it does is that it expresses the free energy of a ferromagnet. Okay, let's say with magnetization M, okay, in terms of a power series. So this F, which is a function of M, can be written as a summation of this term. So F0 plus A T M square plus B M to the power 4 plus dot dot. Okay, so this is my equation number 1. Okay. Okay, any question on this? Okay, so this is a constant term, and this coefficient AT, this is temperature dependent. This one is not a function of temperature. Okay, so I am hoping that most of you have studied this thing already, so that's why I am not getting into too much details, but I hope that you have understood whatever is written so far, right? Okay, so now the question is, why am I considering only the terms like m square m to the power 4? Any answer? Anyone? Question, why the m term is missing? Anyone?
So because it is a Taylor series expansion.
And in Taylor series you don't have m term, or it's the first order term you don't have, don't you?
Sir, in the first order,
energy is minimum, then the
Huh?
first derivative will vanish.
No, can you repeat?
Sir, because the energy is minimum, so the first derivative will vanish at that point.
No, that is something which we will solve to find out. Okay, so let's say why no m cube term? No one? Anyone has any answer? Okay. So the reason is that basically this is true for, or basically let's say it's a okay, it's a general model with Ising symmetry. Okay, so what the reason why I don't have any of these terms is because, let's say if I have this state, okay, or I have that state, okay, so both are saturated state and are supposed to give you a ferromagnetic behavior, right? So you have an up down symmetry, so the energy should not be different because of that. So whether it is in up or in down configuration, the free energy should be same for both. Okay, so if you have any odd term, let's say m or m cube, then that will not be true, or that will not basically hold true. Okay, is it clear? No?
So then m and m cube.
Say?
Sir, then m cube to the power 5, all the terms cost the same amount of free energy. That's why.
Okay. Let's say I have a magnetization that is, so let's say all are like this, okay? That gives a magnetization plus m, okay? If
Yes,
they are
sir.
like this, then the magnetization will be minus m, right? Okay.
Yes, sir.
Now ideally these two configurations are identical, right? They're degenerate configurations if there is no magnetic field, right?
Yes, sir.
So the energy of this and energy of that should be identical,
Yes, sir.
right? So now if you have a m term, let's say f0 plus some coefficient, let's say c times m plus am square, okay? So let's say if this is the energy for plus m, then for minus m this will be minus cm, right? But for the square
Okay,
term
sir.
this problem will not arise. Okay,
Yes, sir.
requires only even terms to be present. Okay. Okay. So I hope that part is clear. Okay, chalo. Okay. Let us focus on our lecture. Okay. Okay. So now here, as we said that this AT is a function of temperature, and B it is not a function of temperature, and usually we assume B to be positive. Okay. If we expect to have a phase transition, then basically, so here phase transition means ferro to para, okay, then this AT has to change sign, okay. Okay, so now we will define Tc as the critical temperature. Basically that is the temperature where we have phase transition, so AT will also change sign around that point, okay. So near T equal to Tc, let's define AT equals A0 times T minus Tc, okay. So as you see here is that if T is higher than Tc, then this will be positive. If T is less than Tc, then it will be negative, okay. Okay, now to find the ground state, what do you have to do? Sambit?
Del A del T
We have to
equals to
minimize
0.
Yes, sir.
free
Minimize the
energy.
free energy. Yeah.
Okay, how will you do that?
Del A del F del T
You
equals
have
to
to
0.
Not T,
check
here M is the one.
Yes, sir. Magnetization.
Yes. Okay. So if we do that, so we have the expression here in equation number 1, and if we do that, then what we will get here is basically 2m times A naught T minus Tc plus 2bm square will be equal to 0. This is my equation number 2. Okay. Now as you see that the left hand side is a product of two terms. Okay, so we have a m and then these square bracketed terms. So right hand side is 0. That means that each of these terms have to, or it could be 0. Okay, which means that each of the LHS terms could be 0. Okay, so one option is basically m equal to 0. Okay, and another option will be m will be equal to plus minus square root of a0 tc minus t divided by 2b. Okay, now if you look at m equal to 0 means that magnetization is 0. Okay, so that can only describe the system when the temperature is above critical temperature. Okay, commonly. Okay, so let me write it down. So m equal to 0, this is usually, or this is always valid at T greater than Tc and a position of unstable equilibrium at T less than Tc. We will see this very soon. Okay. Okay. Now the second solution where you have m equals plus minus square root of a0 Tc minus T divided by 2b. Okay, so this is only valid at T less than Tc. Can anyone tell me why is it only valid at T less than Tc?
Yes, sir. The under root term will be negative, so it will be complex.
Yeah. So it will be an imaginary number. Okay.
Yes, sir.
Otherwise, we have to basically deal with square root of a negative number. Okay. Okay. So now what's the first thing that we do is that so usually I think in your class 12 mathematics you have solved these extremum problems, right? Maximum or minimum you have found. Okay, so you know that if you want to find the solution, or let's say the first derivative will only give you solutions that could be positions of extremum. That means it could be either maxima or minima, right? But if you want to know whether it is the position of minima or maxima, then we also have to take the second derivative, right? Okay,
Yes,
so
sir.
what we'll do is that we'll take the second derivative. So I'm not solving it exactly, but you will get this answer 2a0 times t minus tc plus 12bm square. Okay. Okay, so let it be, I think so. This is 2. This is my equation number 3, and then here this is equation number 4. Okay. Now if m is 0, then del 2f del m2 will be 2a0 t minus tc. Okay, because the second term will be 0. Now this is greater than 0 at t above tc. Okay, and this is less than 0 at t lower than tc. Okay, so what does that mean? This is a, so if it is positive, if second derivative is positive, that means what does it tell you?
It's paramagnetic.
No. Is it maxima or minima?
Minima.
Minima.
Okay, and if it is greater than, so less than 0, then it will be position of maxima. Okay. Okay. So for m equal to 0 at temperatures above critical temperature, it is a position of minima, which means that it could be a stable solution. Okay. But below Tc, it is a position of maxima, so it is an unstable solution. Okay. Now let's say if we come to the other solution where m square is basically a0 tc minus t by 2b. Okay, so there del 2f del m2, if you put this value, it will come out to be 4a0 times tc minus t. Okay, now this is greater than 0 at t less than tc. Okay, and it is less than 0 at t above tc. Okay, so this is a position of minima and this is a position of maxima for temperatures above critical temperature. Okay, is it clear? Okay. Now what we will do is that we will try to see how the free energy curve looks like. So on y-axis we have f of m, on x-axis we have m. Okay. Okay. So this is the curve which you find at t above tc. Okay. Now let's say if my temperature is lower than tc. Okay. So this is t less than, sorry, this is not t less than tc, this is actually t equals tc. Okay. Now if my temperature is lower than this, then what I will have is that Okay, completely gone. Okay, so this is T less than Tc. Okay, so as you see here, I have, this is one position of minima and this is another position of minima. Okay, so let's say this is my minus m and this is my plus m. Okay, so these are non-zero solution and this point is m equal to 0. Okay, so if you look at it, so you see that at t above Tc we have only one solution, that is m equal to 0, which means that there is no spontaneous magnetization. Okay, but if the temperature is lower than the critical temperature, then we have a non-zero solution. Basically there are two solutions, either plus m or minus m. Is it clear?
Yes, sir.
So this is what we are getting from the second derivative. Okay, so if you look at the second derivative here on this slide, then for m square equals this non-zero solution a0 Tc minus t by 2b, the position of minima, I mean this solution is the position of minima that we are getting from here, and that's what we are seeing also here. Okay, but m equal to 0 solution is a position of minima for t above Tc. Okay. Okay, so now if you want, you can also plot this thing in MATLAB or similar plotting packages, and you can see you will get the same kind of behavior. Okay, now if I plot m as function of temperature here, then here what I will get here is that something like this. Okay, so this dependence will be proportional to Tc minus t to the power half. Okay. So where from I am getting this? I am getting it from this expression, m square equals a0 times Tc minus t by 2b. Okay, so here my m, it goes as Tc minus t to the power half. Now if you remember, we have the this critical exponents. So here this exponent is beta, so the beta here comes out to be half. Okay.
Yes, sir. Yes, sir. I understand the graph.
Understood the graph. Okay, now tell me how come I am getting this expression that this right hand side graph, it goes as Tc minus t to the power half. I wrote this expression here.
Yes, sir. From
This expression.
that expression, this is between that m versus t.
Yes. You need to be more attentive. Okay.
Yes.
Okay. Chalo. So what do we learn from here? So we get m equal to 0 as the solution for t above Tc,
Sir,
and
sir, what will be the behavior at t equals to 0?
t equals to 0. Very good question. What do you think?
Sir, it will be square root of a naught Tc by 2b, like m value.
Yes, so basically it will, this t will be gone, so it will be a0 Tc divided by 2b. So whatever behavior you have at t less than Tc, something similar will be there. Only the value of m will change. So this graph, which is at t less than Tc, this is valid for all temperature below Tc. Okay.
Okay, sir.
Okay,
Yes,
but
sir.
having said that, keep in mind T equal to 0 Kelvin or the absolute zero temperature, okay, is always a very special point. Or give me a second. Sorry. So T equal to 0 Kelvin is a very special point because this is something which is very difficult to achieve experimentally. Okay.
Yes,
So
sir.
we exactly don't know what will happen at T equal to 0 Kelvin exactly, but let's say some non-zero value very close to like even like nano Kelvin temperature or something, this will be valid. Okay.
Yes, sir.
Okay. Okay. So as you see that this Landau's theory is also a mean field theory approach. Okay. Can you tell me why is it a mean field theory? Because here also the spins fill an identical average exchange field produced by all the neighbors. Okay, so this field is proportional to our magnetization. So this approach is also identical to Weiss model. Okay. Okay. So now as you see that if T is less than Tc, then M equal to 0 is an unstable solution. Okay. Now if sorry. So let's say this is my M versus T graph. So I can have two dependencies. One is let's say plus ms and other is minus ms. What is plus and minus? Basically this is plus and this is minus. Okay. Okay. So basically at T less than Tc, M equal to 0 is an unstable solution, and these non-zero solutions both are equally probable. Okay, and stable solution. Okay, so let's say if one wants to move from plus m to minus m, then we have to apply certain energy. Okay, so if one wants to move from m equal to plus m to m equal to minus m, energy has to be provided. Okay, so this is clear, right? So what I'm saying is that let's say I have the system here, or let's say this is my stable solution. So if I want to change the configuration to minus m, then what I have to do is that I have to apply a certain amount of energy to overcome this barrier. Okay, so one of the ways I can do is by applying a magnetic field. Okay. Applying a magnetic field will create an asymmetry, or let's say it will prefer one, either plus m or minus m, depending on the direction of field. Okay, so either it is plus h or minus h. Okay, so in that case transition will be possible. Okay. Okay. Is this part clear what I said? Yes or not?
Yes,
So
sir.
why you are taking plus small h and small?
No, H is the magnetic field. Okay. The reason why I'm saying plus H or minus H is again it's the direction basically.
Okay.
Like if I consider direction like field along a given direction as plus H, then it's basically I'm not using any vector here. So it's basically like, how can I say, like you know the energy will be mu dot B, right?
Sir, the small h is equal to mu into h, I think, from Ising model. So from that we can say that the direction of the magnetic field is given by
So
h. Yeah.
here actually we are writing I think both M and H. Okay. But the thing is that, okay, so don't go by this plus H and minus H, is basically just to say if the field is in one direction or it's in the opposite direction. Okay, it is same like plus M or minus M. As you can see in the solution here in the graph, that basically this plus MS or minus MS, they are both identical basically. It's a mirror symmetric configuration. Okay. 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 So now what else we can do using the expression for Fm, one can calculate entropy S, which is basically minus df dt. Okay, specific heat Cv will be T times del S del T susceptibility which is del M del H. So of course H has to be present here in this case. Okay. Now another thing what we can do here, as we know that the critical exponents, they are also related to these values. Basically critical exponents are related to them by, so m goes as Tc minus T to the power beta. Okay, susceptibility is goes as T minus Tc to the power gamma for T above Tc, then goes as Tc minus T to the power gamma at T below Tc. Okay, m goes as h to the power 1 by delta, and specific heat, it goes as T minus Tc to the power alpha. Now we know this value of beta is half here. Okay, gamma will be 1, delta will be 3, and alpha is 0 here. Okay, now all these values are taken here from Weiss model. Okay, we can also calculate some of these values for this case. Okay, so let's say, so we already got the value of beta. Okay, so let's see if we want to know the value of delta. So what we do is that we will consider this system in the presence of a magnetic field. Okay, so the free energy I can write Fm will be F0 plus A T m square plus Bm4 minus m times h. Okay, so this could be plus mh also. Okay, okay, right. Now if I do the minimization, then my del f del m will be 0, which will give me 2a0 t minus tc times m plus 4 m cube b minus h. Okay, so now if we go close to tc, okay, then my m is small. Okay, as you see here, very close to tc, my m is small. Okay, so we will ignore the higher terms. So you will ignore m cube term. So what we'll get here is that 2a0 t minus tc times m will be of the order of h. Okay, okay. So I am going. Yes, okay. So now if I take del m del h here, so that will go as 1 by 2a0 t minus tc. Okay. Now del m del h is basically nothing other than the susceptibility. So this will go as t minus tc to the power minus 1. Okay. So that tells me my gamma is equal to plus 1 here. Okay. Okay. Now coming back to this expression again, if I want to find out the dependence between let's say m and h, okay, so then what I'll do is that I'll again take this expression. So it's basically tells us, let's say again, okay, so it's that 2a0 t minus t m. Okay, so what I can write here is that m times 2a0 t minus tc plus 4bm square equal to h. Okay, now close to tc, I'll drop t minus tc because this will close to 0. Okay, so what I'll end up with is that 4b m cube will be of the order of h. Okay, or m will go as h to the power 1 by 3, which means that my delta will be 3. Okay, so earlier I have got beta equals to half, now I have got gamma and delta. Okay, so basically we can also get the critical exponents from this expression also. And the good thing is that these values match exactly with the values which are predicted from the Weiss theorem. Okay. Okay, so this briefly describes this Landau's theory. Now there are actually a lot more which can be said from here, but let us just see what we have done. So remember that we have so we want to describe the behavior of a ferromagnet and the phase transition. And what we have done here is that without getting into the details of the system, we have just considered a free energy functional, and from there, by way of just optimizing, we are able to find out the ground state, different solution, phase transition, critical exponent, and all these things. Okay. Okay. So now, if we come back to this graph, then we see is that at t greater than Tc, this is basically a parabola. So m equal to 0 is the solution. That means there is no spontaneous magnetization. There is the paramagnetic phase. Okay. But when T is lower than Tc, then we see that there are two non-zero solutions. One is plus m and minus m. Okay. So that is possible because my system has a up-down symmetry. Okay. And m equal to 0 is a unstable solution here. Okay. So if I want, I can go from plus m to minus m or minus m to plus m, as it's the energy curve. So you can see I have to cost certain amount of energy. Okay. So that can be done through applying an external magnetic field. So if I apply the field, then this symmetry will be broken. Okay. So here what we have seen is that basically the okay. So if I know the free energy, then I can also find out these thermodynamic quantities and also the critical exponents. So beta, gamma, alpha, delta, and the values which I'm getting here are also matching with the values which I got from the earlier OS theorem. Okay. So this is briefly the summary. Okay. So any questions so far on this?
Constant extension. I mean, how we relate? They are identical with the WISE model.
Okay, the reason we are saying it is identical is not the model is exactly identical, but the results which you are getting are matching with that.
Yes, sir. Beta, alpha, gamma, they are matching. But in case of exchange field, how they related? How can we say that they are identical? But we here we cannot consider the exchange field.
Right. Okay. Good. So if you think of that, basically these two approaches are not exactly same, of course. Okay. So in the case of WISE model, what you did is that you consider some sort of internal mean field, right? That is basically the molecular field. Okay. Which gives you some sort of magnetization. Okay. Now the origin of that molecular field lies in the exchange interaction. Okay. Agree?
Okay, sir.
But in the expression, we define BMF through some SI Hamiltonian.
Yes, sir.
Okay. Okay. So there we considered BMF, right?
Yes.
Here, what we are considering is an M, right? So free energy is a functional which is a function of M.
Yes.
Now, if M is 0, then this free energy is nothing but a constant term, which will tell me nothing, right?
Yes.
So this expression makes only sense when M is non-zero. Now, in which case I can expect M to be non-zero? When there is a BMF, right?
Yes.
So in the expression there is no magnetic field, which means that no external influence is acting upon to align it or to give a non-zero magnetization. So in the absence of any field, the system is giving you a non-zero magnetization, and it's an Ising symmetry. So it is only possible if there is an exchange interaction.
Okay. For non-zero magnetization.
Yes.
Okay.
So you can indirectly it is a similar kind of thing, but the approach is different.
Yes. So I mean, we can say from this Ising symmetry, we can say they are creating exchange field.
No. The exchange field is there already. Okay. But Ising symmetry we are considering because the model we are considering is basically that type. Okay. See, very simply the reason I am telling you Ising symmetry because